Welcome to the ET380 lecture video for PN junction diodes and special diodes. Here's a standard junction diode. It can be either a power or a signal diode. Here we show our PN with our PN junction. When it's forward biased, we get current flow. When it's reverse biased, it blocks the circuit. So here's our characteristic curve. Here is our 0.7, or somewhere between 0.3 and 0.5, where our diode starts flowing current, and we lose, or the diode conducts about 0.7 volts across it. So if we were to figure this circuit out, we would, in this case, where it's forward biased, this will be 0.7 volts. And then we'd subtract it from our supply voltage and we'd be able to find our current across our diode. When we go against the diode, we have the knee and an avalanche. Avalanche in a standard diode is when it breaks. So this is an important peak inverse voltage that we could allow without it being damaged. Okay, here are a couple diodes circuits. This diode is reverse biased. When it's forward biased, its arrow points towards ground. In this case, there is no current flow through here, so our current flow is through our meter, so we're going to get 6 volts since it's essentially an open circuit through our meter, so our current would actually flow through our meter. Here it is forward biased, so we're going to get our voltage, our diode with 0.7 minus 0.6. We figure out the current across our resistor to make sure that it's not damaged. An LED is essentially a junction diode. It's doped differently, and it also conducts when it's pointed towards ground. So when we have a voltage through our LED, this guy is going to light because he's forward biased. This one will not light because he's reverse biased. If we want to calculate a circuit for this, we're going to use the forward bias voltage, and 1.5 is fairly reasonable for an LED. So we're going to take our 1.5, subtract it from the 8 volts, and then we could go through and calculate what side resistor we need in order to make this LED. The more current, the more brightness to a limit. Here's a junction diode called a Zener diode, and it's very similar to a standard diode, different doping. And what we have when it is forward biased, it acts like a diode, so it's going to be like 0.7 volts or something in that neighborhood. When it's reverse biased, it will act as a Zener diode, so whatever voltage is on that designed for that diode, it will conduct that. So what we have here is the Zener voltage minus our supply voltage, and then figure out our current. So here's our diagram, and we have standard forward bias, and at reverse bias, at this Zener point, our breakdown voltage, it actually will pass current, but it will be held at the Zener voltage. Okay, here's some Zener diode circuits. We show the Zener diode here. The arrow is pointing away from ground, so it is working as a Zener voltage. So we would take this 5 volts minus from the 6, and we could figure out the current across it. This diode circuit, this Zener here, is forward bias, so he's going to be held at the diode voltage around 0.7 or that range. So it's just a standard diode when it's forward bias, pointed to ground, and against opposite of ground, it is a Zener. Okay, let's look at the varactor diode. It's also known as a varicap diode, a variable capacitance diode, a variable reactance diode, or a tuning diode. Here's a symbol here, a diode and a capacitor symbol together. Here I'm showing 2 varactor circuits. So what we have here is a special diode And based on the bias that we put on here, if we add voltage in reverse, our dielectric widens, which changes our capacitance. If we put a lower voltage on it, our dielectric narrows, also changing our capacitance. So essentially this is a variable capacitor based on our applied voltage in reverse. Okay, let's take a look at the constant current diode or current limiting diode. Here's the symbol, and it is a two-terminal device. Internally, it has a junction field effect transistor with a feedback. So the current is either limited or constant. Here we have a Schottky diode, and here's the symbol for it down here. And it is not a p-in junction. It actually is metal and N-type material. And this device is used for very fast switching. Here's a pin diode, and it's received its name from the way that it's set up. So we have p-type material, intrinsic material, which is pure silicon, and N-type material. Here's our symbol, and it is used in mostly microwave frequency application. It has a variable forward series resistance, and it's used for attenuation, modulation, and switching. In reverse bias, it exhibits nearly constant capacitance.